right producers, so all the internal services and databases. On the right-hand side, you have the consumers, so internal services again, our Surge computation system, ELK for application logs, Samson Flink for stream and real-time processing. And at the bottom, you have the ETL into Hadoop and Vertica and Hive for the batch jobs. And so Kafka really is the backbone of most of our data analytics. Like all the data that flows into the analytical side of Uber flows through Kafka. Today, I think I'm going to focus more on inter-service messaging, since this is the microservice meetup. But before I do that, a little word on scale. Kafka, as I mentioned, basically all of the messages that end up in Hadoop have to go through Kafka first. And so we operate trillions of messages per day. That amounts to petabytes of data volume per day. We have tens of Kafka clusters, each of which have hundreds of brokers apiece, and ranging over tens of thousands of topics. Okay, so let's discuss the more interesting part of this talk. What is messaging? So how many people here use Kafka? Okay, so about maybe half. How many use another messaging system? RabbitMQ, ActiveMQ, SQS. Okay, so another half. And the halves don't quite match. But so I think I'll touch on kind of how I think of messaging and messaging-like semantics, just so that we can get everybody on the same page. So in my mind, messaging can be thought of in two large buckets, streaming and queuing. So what is streaming? Streaming is generally thought to be ordered, by which we mean if you have a stream or partition, you can receive a message, and you can commit that commit that offset, and so then you will no longer receive message 7. Message 7 has been successfully processed, the cursor increments to 8, and you continue processing in order. And so because streaming is an ordered stream of messages, Kafka and streaming systems in general like to give you a commit up to API for committing your messages. And so what commit up to means is that if you receive a batch of messages, in this case 7, 8, 9, you can commit offset 9, which actually marks offset the messages 7, 8, and 9 all successfully processed. And so the cursor bumps to 10, and you don't receive messages 7, 8, 9 again. And in Kafka in particular, the scale-out strategy for Kafka is partitions. And so if you have a single Kafka topic, the Kafka topic can actually be split into multiple partitions, 0, 1, 2, where each partition is an ordered stream. So it's important to note in Kafka in particular, you don't actually have guaranteed ordering across multiple partitions. And additionally, because ordering is a pretty important concept in Kafka, each partition is assigned to at most one consumer instance. And so in this case, if this consumer application on the right has 2 instances, each partition can be assigned to at most one consumer instance. So you notice that, for example, partition 1 is not double assigned. Now queuing. Queuing is probably what most people think of when they think of inter-service messaging, because it offers easier semantics to work with. I put a little asterisk next to queuing because, at least for our use case, we're looking more at single publisher, multi-consumer queuing, right? Not single publisher, as opposed to single publisher, single consumer queuing. But many of the definitions here still hold. So queuing generally is thought to be unordered, which is easy enough to understand. You have some messages here, the little green check marks indicate that they have been acknowledged. And so in Kafka, you would get 4 first. In the queuing system, you might get 6 first. And because messages are generally unordered, commit up to no longer works, right? And so queuing offers you ACK-NACK semantics. And so message 6 was delivered, so you can acknowledge message 6 independently without also acknowledging 4 and 5 along with it. You can also, in many queuing systems, you can also NACK a message. And by NACK we mean, say in this case, message 4 gets delivered and you fail to process message 4, say timed out, or a downstream dependency was unavailable, or you just, I don't know, something went wrong. You can NACK message 4, here denoted in the queue by red X. And that means the queue knows that message 4's processing failed in some manner, and many queuing systems will redeliver this to you. But first, let's move on. Message 5 will get delivered to you, because why not? Right, okay, so what happens with all the messages that were napped? These were messages that were unsuccessfully processed, and so naturally you want to process them again. And so queuing systems generally offer redelivery and DLQ semantics. So redelivery means, okay, message 4 failed to process, and so sometime in the future I'll give you message 4 again, and maybe now things got better and you can process message 4. But wait, it didn't work, so you want to nap message 4 again. And so you can kind of repeat the cycle a few times, often configurable, and eventually, I mean, if message 4 fails a million times, you don't really want to get it back again, because why would you want it back? And so messaging queues generally mark this, or put this into something called a dead letter queue, which is somewhere where bad messages go, and the operator usually goes and introspects their dead letter queue and says, okay, let's see what has landed in the dead letter queue after some configurable amount of failure, and then they can choose to see the message again or not. Right? And so dead letter queues, I'll explain that later. But okay, and finally, because as you depicted in this picture, queues generally don't queues have different varying semantics for scale out, but a queue generally presents a competing consumer model, by which we mean a single queue can have multiple consumer instances subscribed to it, and a disjoint subset of these messages gets sent to each consumer instance. So in this example, the single queue has 2 consumer instances, and messages will be partitioned between the multiple instances. And of course, this is possible in queuing as opposed to streaming because there's no ordering guarantee. So from a high level, why streaming? Right? Streaming, Kafka is very stream-oriented. So why streaming? Streaming is very useful with data analytics and stream processing, right? If you want to do a select star aggregation over the last 10 minutes to count the number of page clicks or something, right? That's very stream-oriented. It's also very useful for event-driven architectures and event sourcing. So if you want the event stream, you want to know, like, there's no point to have the user sign out before the user signed in. And so having the ordering guarantees of streaming is very useful in these scenarios. And of course, log aggregation is an example of event-driven architectures. And finally, in the case of Kafka, or in general streaming, scalability is easy because you just have many small streams. Why queuing? Queuing, at least for inter-service messaging, communication between microservices offers a much more friendly API. Right? So you can acknowledge a single message without acknowledging all the messages, because often for throughput you want to take a batch of messages. In Kafka, when you get a batch of messages, you have to commit the whole batch, as opposed to saying, oh, this one succeeded, this one failed, et cetera, et cetera. It often allows you to have non-blocking retry, so if you knack a particular message, you can still receive newer messages while that message is still being retried. Something which our customers really wanted, our internal customers really wanted, was somewhat decoupling consumer and producer scale out. So they wanted to be able to scale their consumers independently of scaling the producer. In Kafka, the unit of scale is a partition, so if a consumer wanted more throughput, in other words, more workers, we'd have to increase the number of partitions, which then means the producers will also catch this increased number of partitions. And oftentimes the consumer, especially one that has a lot of computation or is waiting a lot on downstream network requests, may take seconds to process a message. Producer doesn't really need to have that much scale, that many partitions. And of course, it also allows queuing systems, the competing consumer model in particular, allows you to have elastic consumer scale out. So a consumer can elastically increase and decrease the number of workers as it sees fit, depending on the requirements at the time. So at Uber, we wanted to see whether we can capture some of these queuing-like semantics in Kafka. So the requirements I've kind of described in the definition before. We wanted ACK-NACK semantics. We wanted redelivery. We wanted delay between retries. So when a message is nacked, users want to say, okay, please send this message back to me sometime in the future, like 5 minutes from now, or 10 seconds from now. So it's some degree of back off. Dead letter queue, this is a place where messages go after they have failed some number of times. And on the dead letter queue, users generally want to purge and merge. So purging means, okay, I've looked at the dead letter queue, these messages are bad, and so let's just get rid of them. Merge means, okay, I've looked at these messages, I fixed whatever bug, my JSON parser wasn't working or whatever, and now I want to read these messages again so I can process them. Competing consumer in some limited fashion. something we didn't quite define, but we run multiple data centers at Uber, and so they wanted seamless failover between data centers. And we have many different programming languages at Uber, so we needed to write this to make this available for people in Go, Java, and Python. Why Kafka? As there are many other messaging systems, the _NQs of the world. Apache Pulsar, which is an interesting new project which offers streaming and queuing semantics on top of a messaging bus. And we could just build another one from the ground up. But we chose to use Kafka because we have been using it for many years. It's been tested, proven to be reliable, it's proven to be highly performant, and I guess most efficiently the data is already there. Right? Everybody's already writing to Kafka, so why not try to create more user-friendly semantics for the data that already lives in Kafka? And additionally, there's a reduced operational and engineering costs by not having to maintain multiple systems. And so our design focused primarily, because Kafka's consumer story is generally pretty client-side focused, right? The client is, one of the client instances gets elected as a leader. The coordinator is on the broker, but the leader decides a partitioning scheme. The leader decides which consumer worker gets which work, and so we decided building this into the client side really made the most sense given Kafka's consumer side story. And so we built this into Go and Java clients. And so if we look at how we did it, the native Kafka consumer, say you have a single topic, the messages flow to a single consumer process. Okay, this is how Kafka works. If you use any of the open source Kafka libraries, this is how you would get your messages. So the first thing we wanted to do is, okay, can we introduce competing consumer? Well, yes. We can just create some number of threads in this consumer process. And so each consumer process, which is our internal library, spins up some number of configurable amount of threads or Go routines, depending on whichever language you're in. And these threads offer some limited form of competing consumer. Right? By limited, I mean, sure, it doesn't give you, because it's thread-based parallelism, this is generally more useful for I/O-bound workloads. If the CPU is busy, then no additional threads can be scheduled, and that's not very helpful for you. But based on our user studies internally, the majority of workloads in a microservice-based architecture is I/O bound. You're waiting for your 10 different downstream dependencies to get back to you. And so this is good enough for our users. And so again, in this case, maybe a little more complicated example, you see that this consumer instance has 4 threads, and so messages that flow in get dispatched to these threads. So let's dive a little deeper into the messaging flow, because that kind of explains how we implemented the AppNac semantics, which is a little more difficult to do. So in the messaging flow, you have a single topic partition, messages come in. And in the consumer library, we have this thing called the in-flight offset tracker. And so when a message comes in, the first thing it does is gets put into this in-flight offset tracker. So these are messages that the library has seen, but the worker threads at the bottom, the gray worker threads, haven't actually seen these, and so this is how we track what messages have flown through the system. And so the first thing we do is we put all these messages in there. Okay, so we've seen message 3, 4, and 5. Then the consumer library, this big blue process, dispatches the messages it can to the workers that have no work. And so these 3 threads get the messages 3, 4, and 5. Let's take a look at the in-flight offset tracker. So really it's just a buffer in which as messages come in, the messages are put into the buffer, right? So 3, 4, and 5, and 6 messages, these 4 messages get put in the buffer and then are dispatched to the workers below. Now maybe message worker 4 finishes processing first, so message 5 is acknowledged. And so we mark the messages acknowledged in the buffer, but we cannot commit yet because 3 and 4 are still being processed, so we need to mark, we can't commit. But it's interesting to note that we don't do header line blocking here, right? So the buffer has one additional space, and so message 7 can now come in, it gets put into the buffer, and then consumer worker 4 can continue processing message 7. Then, okay, maybe another message 4, offset 4 gets successfully processed ACT, and so we mark it as successfully processed. Now, this is interesting. So message 3 now gets NACT. So first thing to note here is 3, 4, and 5 have now all been processed successfully or not in some fashion. But we can't simply acknowledge or commit up to 5 because then message 3 might be gone. So we do the most simplest thing you can imagine. We just store message 3 somewhere else. So message 3 gets written, produced, in fact, to a separate Kafka topic, which is the retry topic. And so it might be a little hard to see, but this is actually message 3, right? But it's written to a new topic, so in that particular topic, it's assigned, say, offset 0. But we store the metadata, so we know that it was originally message 3 from some other topic. And so once it's been produced successfully, we can commit up to 5, because 3, 4, and 5 were all live somewhere safely or have been processed. And so we can increment the committed pointer, and this is how we do our acts. So, redelivery. Well, putting it into a Kafka topic has one obvious benefit. Redelivery is very easy. I just read from the Kafka topic and poof, the message appears again. Now, delay between retries. That's an interesting one. So some of our users wanted delay between retries, and so what this means is that if a message fails, they want to say, okay, please redeliver this to me sometime in the future. With Kafka, it's really hard to do per message delay because messages in a partition are ordered. So we impose the additional restriction that a user is only allowed to specify a fixed delay for a topic. And so, for example, this topic will have a delay of 5 minutes. That means that if I knack a message, I can guarantee that this message will not be delivered to me within 5 minutes of the time I knacked it. And because Kafka guarantees ordering, we know that if message 0 is read in and it's too new, in other words, if the 5 minutes has not elapsed, we can just sleep or pause that particular partition consumer. And message 1, we know because it's necessarily an newer message, should also be slept or should be paused. And so we can implement reasonably efficient delay between retries without some indexed data store. And surprise, surprise, dead letter queues are implemented exactly the same way. We just dump it into another topic called the DLQ topic. And to merge a DLQ, you just delete the topic. The data gets cleaned up by Kafka. To merge a DLQ, you simply, the user, so we have a server that manages the lifecycle of these processes, and so the user simply says, okay, I want to merge this dead letter queue, and the topic, the lifecycle management service reads from the dead letter queue topic and just copies data into the retry topic. Then it'll naturally flow back into the consumer process. Okay, so the other thing that we implemented to make messaging both more reliable and easier for our users is a multi-data center consumer. And so since we operate in multiple data centers, I'll go over the high-level picture of how it works. At Kafka, at Uber, if we have 2 data centers, we have regional Kafka clusters in each data center, and then we have uReplicator, which is our open source in-house version of MirrorMaker, read data from regional clusters and write them to aggregate cluster, right? So aggregate cluster has a global view of the data. But along the way, MirrorMaker actually snapshots the regional to aggregate offset mapping. And so by doing so, we're able to fail over the consumer while synchronizing their offsets between data centers. So consider this example where you have a consumer active in one data center, and it decides to fail over, right? So it turns DC1's consumer off and turns on DC2's consumer. Since it's reading from aggregate cluster, the offsets are not actually synchronized, right? So when it fail over to DC2, it'll resume from whatever offset it previously was at, or the oldest offset or the newest offset, depending on whether any offsets have been checkpointed. But actually, the first thing we do is we get this offset sync service to synchronize the offsets. And so we read the last checkpointed offset in DC1, and then do some translation by mapping it back to the regional offsets, translating it across, and then finding the safe offset to resume from in DC2, and then we push those offsets into the K10 offset store, and then the consumer can simply resume or start the consumer in DC2 and have its offset be reasonably synchronized. And finally, we built this into our Go and Java libraries, and we have some limited support for Python legacy users internally. And so for those who are familiar with Go, the additional thing that we did here was that we kind of broke with the tradition of channel-based consumers for Go or poll-based consumers for Java, and rather tried to present a handler-based interface for our users. And so that means, like you do with your gRPC, RPC frameworks, you register a function, you register a handler function. In this case, it's a function that takes a byte array, and then some parameters for which topic and how you want to consume it. And then you just register it to the consumer, and then you call start on the consumer. And the consumer library seamlessly receives data from the original topic, receives data from the retry topic, it writes back to the retry topic of the DLQ topic, it receives data from the DLQ topic, etc. And so basically, all of the complex how do I deal with Kafka is abstracted away from the user here. And all the user has to do, all the user has to do is specify a function that we call on their behalf. And because ordering is not guaranteed here, we don't really need to worry too much about how do I make sure that they're receiving the right messages at the right time. And so maybe a little bit on future work, current and future work. So we do want to open source some of these implementations. So the Go client library is being semi-actively pushed into GitHub from our internal repos. The Java one is less, not yet. So hopefully, sometime in the next H2, we can find enough time to at least fully open source one or the other. And some other interesting ideas that I have for future work in this realm is something a lot of our users have been asking for is async RPC. And so internally, people use, if people are trying to send synchronous RPCs between microservices, they also want to be able to seamlessly swap and send Kafka messages instead. And so somehow integrating that into our RPC frameworks is something that will bring a lot of value to our users. And in fact, actually that brings an additional step up from here is that even better would be if you are able to send a synchronous RPC, so an HTTP request or a gRPC request, except on failure or timeout or whatever of the service that you're calling, the RPC framework automatically buffers these failed messages into, or failed requests into Kafka, and then you can have the RPC framework replay these messages back to the service that you're trying to call. And you can, of course, you have to elect to do so, but some of our users have really requested this feature because they don't want to manage their own, the service I'm trying to call fails, and so I will back off and retry and manage the state internally, or cascade the failure back to my upstream. But if you can push these messages, these failed requests into Kafka and have some framework periodically attempt to replay these messages back onto the service. A lot of our users have also requested runtime offset sync, and so at Uber we kind of operate Kafka as a service. And so a lot of our users want to say, okay, I have a Kafka consumer running, can I please reset my offset to 10 minutes ago? Or I want to rewind my offset to 2 hours ago. And that's a little hard to do because a lot of the Kafka consumer implementations maintain an in-memory version of the offset it's read until, and so either we'd have to rewrite the consumers from scratch using simple consumer, or I don't know, port some of these features back into the open source libraries. I mean, the open source libraries, especially the Java ones, kind of have this in that you can reset your offset. There's some function to do so, but again, our users really want this hands-off experience. I just register my function and everything just works. Another thing that we've been often requested for is active-active multi-DC consumers. So the multi-DC consumer that I just described to you is active-passive, and so the resources in a single DC are, in the passive DC aren't really used, which is fine if the number of DCs you have is fairly low, but if you go to like 10 data centers, obviously you don't want 1 DC active and 9 passive. So what people really want is to be able to consume from regional Kafka clusters, and if 1 DC fails over, with some policy they can move, have that node be diverted to one of the other data centers, or even better, balance across all of them. And related to this, really, the other real pain point we have at Uber is that because we operate tens of Kafka clusters in each data center, managing clusters, or presenting a federated, unified, like logical view of this is one gigantic Kafka cluster is something that we really want. And so I'm trying to figure out how to do routing between multiple Kafka clusters, and even better routing across data centers. So you can seamlessly fail a topic between clusters or across data centers is something that would be really useful for us as well. I've included some links at the back about the first one's a Go client, which we're in the process of open sourcing. It's been in production internally for about 6 months. So, and people seem to be happy with it, but the features and the APIs have not been fully ported over. We have a blog on our Eng blog about the DLQ retry system that we implemented. And finally, a plug for uReplicator, which is our in-house version of Mirror Maker, which kind of solves some of the rebalance issues presented in the open source Mirror Maker. Thank you. And of course, we're hiring, so if you want to work on these problems, please reach out to me. And if you have any questions, I guess I'm happy to take them. Sure.
I noticed when you were talking about the like retry queue, that you have that based upon like a topic. You have a sort of guaranteed delay for a topic. That was like 5 minutes. But then when you were talking about the dead letter queue and it merged back in, maybe it's just the diagram and making it simple, but does the dead letter queue merge back into the retry queue? And then how does that, I mean, those, as they're added back to the queue, they would be delayed longer than, I'm just curious if you had a policy or configuration for that, or if it was just like, by the time you reach the dead letter queue, just be thankful you ever get it again.
Okay, so for the benefit of people who didn't hear, the question was, in this slide you have delay. You could configure a delay when consuming from the retry queue, but when you merge, you kind of put it back into the retry queue, so does that also get further delayed? And we have internally we have a way of preventing this from happening with some headers, but a perfectly valid answer is also, it's already been sitting there for 24 hours, so 5 minutes is on the other.
5 minutes, yeah.
Sure.
Thanks for the talk. Just wanted to know, so how's that a queue? Because it's still like single consumer per topic from what I can see, or per partition, I'm sorry, right? But basically, we're not sharing any offsets between, let's say, multiple instances of the server or service, right? So I don't see how that is inter-service communication. I think that because there's no independent scaling from what I can see, because the consumer workers you're saying this is like the process and not a single instance of the service. That's not exactly.
Sorry, yeah, maybe it may not have been fully clear from these slides, but each of these Kafka allows you to scale, have multiple processes, as many processes as you do partitions. And so in this case, it's simplified to say there's a single partition P0 here, and so therefore you have a single consumer process C0 here. But if you had 10 partitions in this topic, for example, you could have 10 consumer processes, each of which can have 10 more thread-based workers.
Understood, but that would mean that each would have the same set of messages in the partition, or you're dividing messages in the topic between the partitions. How's that work? Because as in queue, I understand like multiple consumers, right? I don't care about that part. I care about like my messages are there, and then I have multiple processors of that messages, and I don't care which specific instance consumes. I care about the message being processed. That's why I have like try, whatever it is. That's the inter-process communication for me. But from what I can see, like, is there a way to actually have different sets of messages in the different partitions?
So the question was whether you can have different sets of messages in different partitions?
Yeah, to basically have multiple services producing, multiple services consuming, regardless of what's in the middle.
Partitions are different messages. There's no overlap.
If I'm understanding, yes. So there's partitions are disjoint. So when you produce to a topic with multiple partitions, each partition each message gets sent to at most one partition. So you can think of this topic as in fact, the topic is in some senses a big queue. The partitions are just some unit of scale out. Sure.
Can you comment issues you encounter?
Actually, we haven't encountered any serious performance issues here, and we have consumers running at hundreds of thousands of QPS. Because Kafka really scales very well, so as long as you increase the number of partitions, it works pretty well. Additionally, because we kind of do this thing of writing back to Kafka, there's really good locality, reasonably good locality. The biggest problem with this architecture really is that you are copying your data many times over. And so the way of dealing with that is, actually that's another future where currently we just keep a short retention on the retry topic, because we expect consumers to be near the head or the tail. And the DLQ is for 7 days, but not many messages end up there. But just a plug for additional interesting future work is whether we can dynamically scale the retention for a topic based on the current consumer lag. Just another idea.
So here the messages are going to the disk first and then you are reading and processing it?
Yes, since it's Kafka, yes, it will be replicated and put to disk, but Kafka we have not seen any significant scalability issue with Kafka.
So how about you stream data directly into the memory and then you start processing from the memory? So does it help you a lot?
I don't think that's possible with Kafka because it needs to be durably persistent to disk. Additionally, with the retry and DLQ, we want it to be persistent to disk, right? Because if the process crashes, we want it replicated and persisted because we are guaranteeing some degree of retry. Like you can't say, oh, sure, you put it to the retry queue, it didn't actually arrive. Then they'll be really sad that the thing that they expected to be nacked and came back to them never got back to them. So taking a performance hit here for the semantic guarantee is actually worth it. Sure.
How do you actually scale out consumers which are listening to ordered messages in a particular topic, in a particular partition?
Sorry, how
do you scale out consumers in processing messages which are actually sent to a particular partition? Because the messages, let's say I have a requirement for ordered messages, right? How do you scale? Do you have any use cases?
Yeah, so ordered queuing and ordered messages don't work very well in this particular scenario because really if you want the messages in order and per partition order, you can only have at most one consumer instance with one process, one thread. Again, there's some interesting ideas about virtual partitioning by piggybacking the coordinator, but those are really hard to implement. So.
Maybe a basic question, but if you go back to your messages versus queues slide, my understanding of queue is sort of first in, first out structure. So in this case, is it not that kind of a queue, or is it
it's first in, but in queues in the computer science sense, sure, first in, first out. But the MQ systems, maybe first out. Actually, I'm not too sure about whether the MQ systems guarantee first out. But there's definitely ordering is kind of ruined when you have the idea of a retry. Because if you knack a message and it comes back to you in the future, then like really what's happening with ordering. But I'm not too sure.
So inside the queue, what is the time to live? What is the time the queues you set in general?
The question was what's the time to live for these queues? The original topics we run with 3-day retention. The retry with like 1 day and 7 day for the DLQ.
So this is more of a design question. So when do you have to make a conscious decision as to go with your own offset management versus what Kafka provides?
So we actually generally use the Kafka offset system. So assuming you're referring to the slide with the multi-DC active passive consumers, the offset sync service is just a service that sits on top of all active MySQL, was replicated MySQL, master slave MySQL, in which we checkpoint the mapping. So the map, it's like a materialized view of the offsets available inside the Kafka broker themselves. And what in particular we store is that in this particular snapshot, the regional offset A, or 1, was mapped to aggregate offset something else. And then in the other way, we also have from the other regional, we also have the mapping, and then we can reverse compute. But it's not really the source of truth offset store, that still stays in Kafka.
Oh, so you're using Kafka's offset management, but
Yes, we just
right
need
in
some
Kafka, okay.
way, we put it in MySQL so we can easily do some select star, blah, blah, blah. And so.
Regarding the ASIC RPC, are you building something on top of the ERPC plus Kafka?
Yeah, that's a great question. Internally, we have a layer on top of we have an internal RPC framework, so likely that will get put there first. I think our RPC team is evaluating gRPC as a solution moving forward, and so to have it, maybe we need to like collaborate better with the open source community. But for now, we have a nice internal implementation that we can do whatever we want with without worrying about it.
So you mentioned something about inter-service communications for requests. If they fail, they put back on the queue. Is that a separate channel that you're using, not using the same mechanism for inter-service communication?
Yeah, so to be clear, that does not exist.
Oh.
So the question was whether this idea of synchronous RPC backed up by a Kafka-based retry queue exists or not. It does not exist as a solution for our users. I believe some teams that need really high guarantees have implemented something similar for themselves.
So they don't use this primary mechanism.
They do use Kafka as the backup.
As the backup.
Yes, as the backup. But the happy path just synchronous RPC. Cause
Oh,
So I guess we can have to move to the next question. Maybe after that, shall we?
yeah, if you want to ask more questions, maybe find me after.